Okay, hello everyone, Spatiotemporal here. Today I'm going to speak about spatial-temporal data mining, heat map reconstruction, and time series prediction. Firefighters work hard, but how well can they respond to the incidents? That's why they need to work proactively to reduce the number of future incidents. But how? They need to evaluate the past data. But of what data set? The past 5 record event dataset, which is spatial-temporal, for instance, is NTPCFire dataset, containing both the spatial and the temporal features. This is data mined. How can they know if they are working well? The answer is the prediction. But what model is an excellent tool? Deep learning is here to help them. Variational Autoencoder to predict or reconstruct rasterized heat maps. To know where and how many incidents are for the LSTM-RNN of the temporal domain is to forecast a time series of frequency to see how many incidents in a day by observing the prediction trends. An autoencoder contains 2 neural networks, the encoder and the decoder. Both are either FCN or CNN. It starts with an image or matrix converted into a vector, the C vector, using an encoder. After that, the vector set is forwarded to the decoder to obtain the reconstructed image. For the variational autoencoder, instead of the encoder directly forwarding the set vector to the decoder, we need to convert it into the mean and the SD vectors, which can be sampled using the Gaussian distribution into the set vector. Then the set vector is decoded by the decoder to obtain a reconstructed image. The recurrent neural networks, or the RNN, are a class of neural networks that are helpful in modeling sequence data. It is designated to analyze sequential data, like the time series of arbitrary rings. Nevertheless, it has a problem of gradient vanishing as a slicing problem, so the long short-term memory RNN is here to help. It's capable of learning long-term dependencies. It's designed to remember the sequence for long-term periods of time. If you want to know more, consider watching this video. Okay, there are some steps for the implementation. To know more about this, see my IPV file. First, we import the required libraries, as missing libraries can be installed here at the top of the program. In TEMPORAL, you need to update scikit-learn to version 1.0.2. Once the libraries are checked and installed, we may start counting the running time. Then, we need to import the dataset. Here, import the background map and extract only the coordinates and timestamps. Once done, we can plot the points, like this, and split the data frame into 3 years, and do a similar thing. Why are you doing this? Because the rasterization, named the designarization function in the program, can only take 1 year per data frame, and we need to call it 3 times. Once we have done splitting the data frame for the cytogenesis and the designarization functions, we can now extract the temporal domain and convert it to a time series, which looks like this. Then we define the rasterization function, named the designarization, which in turn called the cytogenesis function, giving this visualization. Before our rasterized heat map can enter our VAE model, we need to call the TT-split function and do a relative normalization and display the train and test images. Then we define and call the sigmoid normalization function, because the VAE model has sigmoid as its final activation function. Okay, we will define the VAE model. We right click like this to the left to define the sampling layer to store the set vector, the encoder to preprocess the matrix and convert it into a mean and the SD vectors, and the decoder to convert the set vector back to an image. And here we combine them together into one model. Once we are ready, let's train the model. Okay, once we have done with the VAE, we move on to the LSTM. First, we need to convert the dataset, I mean the time series, to a matrix. After that, we then prepare and process the time series into a processable data. After that, in this block, we design here and train the model and visualize the loss graph. Once the model is trained, we do the prediction, visualize the results, write down below, and calculate the metrics. At the end of the program, don't forget to record the running time. For the free platform, the Colab with no GPU, the Colab GPU, and the TBUCC have no visualization reference or predicted results at all for both the VAE model and the LSTM. Let's analyze the results. We have compared three platforms, namely Colab no GPU, Colab with GPU, and TWCC. The TWCC has the best running time, but it's the hardest to use because it's not free, it's a paid platform. It does the worst at the VAE and does the best forecasting for the LSTM model. For Colab no GPU, it has a moderate running time, did the best at the VAE, but did the worst as the LSTM. The Colab GPU is something in the middle in the term of the VAE model and the LSTM models, but has the longest running time of all three platforms.
Conclusion: TWCC is a paid platform. It provides much better environment than Colab, so it's run faster. However, TWCC is also better for large sequential data. For the Colab, it's a free environment, right? But it's slow. Nevertheless, it's best for small image type data.
And that's the end of the show. Any questions?